Hello! In this video, we'll develop the controller for the multi-cycle processor. So just like we did with the single cycle processor, we're going to work out the controller. Here's the high-level view of it. It takes the instruction and the 0 flag from the ALU in, just like in the single cycle processor, and it produces the appropriate control signals. This time there are a few more control signals, and more importantly, the control signals take on different values on different steps. Let's break that controller down into some sub-blocks. So this is an example of hierarchical design. Instead of having a main decoder that was combinational, we'll now have a main FSM that produces most of the control signals on the appropriate clock cycles based on op. Then we'll have the ALU decoder that's exactly the same as the single cycle processor. It will take ALU op from the main FSM and the funct fields and bit 5 of the op and determine what ALU instruction, what ALU control we need to use. The PC logic will be similar, based on a branch and 0, and on another signal called PC update we will determine whether we want to write to the program counter. So PC update will be true when it's time to fetch the next instruction or when we're doing an unconditional jump. Branch will be true for branch not equal. Finally, we're going to pull the instruction decoder out from the main FSM because the immediate source depends only on the opcode, not on any steps. So that will let us simplify it a little bit. It'll be combinational logic. So let's look more closely at that instruction decoder. Based on the type of instruction, this will put out the appropriate immediate source. So load word had an op of 3, so immediate source should be 0, 0 with that I-type format. Store word is an S-type instruction. Op is 35, and so immediate source should be 0, 1. R-type instructions don't need an immediate, so immediate sources don't care. And branch on equal has an opcode of 99, and so the immediate source would be 1, 0. And the instruction name here, of course, doesn't actually mean anything to the truth table. It's just to make it easier for the human to read. This is simply some combinational logic that looks at the 7 bits of op and produces 2 bits of output. Now, let's design the multi-cycle main FSM. So again, it's taking the 7-bit op and it's putting out the write enables. So that would be reg write and mem write, just like before. Also IR write to tell us it's time to update the instruction register. And the things to change the program counter, branch and PC update. It also puts out the same control signals to the multiplexers, ALU source A and ALU source B. Now there's a little bit more to choose from, so these are each 2-bit control signals. Address source is the address input to the memory, and result source to choose which result to take to write back. And of course, ALU op encoding was 0, 0 for add, 0, 1 for subtract, and 1, 0 for look at the function. So this is a lot of signals to write, and they're going to be a state machine generating these signals. To declutter the FSM, let's have some terminology for these write enable signals. Here, we will just list their name if they're asserted, if they're 1, and if they're not asserted, if they're 0, we'll omit them from the state. The multiplexer select signals, if we care about them, we'll list their value. If they don't care, we won't list them. So, we said the first step in any instruction was to fetch it. So on reset, let's have the main FSM go to a fetch state, called state 0. And in that state, the program counter is ready for us. We need to choose it from the address source. So address source needs to be 0, right here. Based on that address, we read the instruction out of the instruction memory, and we will write it into the instruction register by asserting the enable signal IR write. So we need to make IR write true. Nothing else is happening in the data path, so that's all we need to do in state 0 right now. On the next step, we're going to decode the instruction and do the sign extending. So the instruction is sitting right here. We'll take bits 15 through 9 of it, feed that to the register file, and read out the value of RS1. We'll take upper bits and feed those to the sign extender and get out the sign extended immediate. That immediate depends on IMM source, but remember IMM source is determined by the instruction decoder. It's just combinational logic based on the opcode, so we don't need anything in the state machine to handle that. So actually there's no control signals at all needed in this state. We just give time for the register file and the sign extender to do their business. Alright, so that was decode. Next, depending on the instruction, we'll go and do the third step. So if the opcode is 3 for a load word, then we need to do the load, and the first step of a load was to calculate the address. We need to add the first source to the immediate. So the first source is sitting here. We need to choose it with this multiplexer. So we need ALU source A to be 10. The second source is coming from the immediate. We need to choose this terminal of the mux. ALU source B needs to be 01. Pass those to the ALU, and we want the ALU to add. Remember, an ALU op of 00 tells the ALU always add. So now we get our answer, and we'll store it into the ALU out register at the end of step 3. In the fourth step, we need to actually do the read from memory. Now it's getting too cluttered to show both the FSM and the data path on the same slide, so we're going to break it into 2 slides. But when we're doing a memory read, we will set result source to 00 and address source to 01. Let's look at that on the data path. So we have our address sitting in here. We need to choose it. So result source needs to be 00. We'll bring that result around as the address to the data memory. So we need to make ADR source be 1 to choose that value. We go read from that address in the data memory, and we get read data out and store it in the data register at the end of step 4. Finally, it's time for step 5. So it's time to write the result back to the register file. And in this step, the value is sitting in the data memory. We need to choose it. So we'll go into the result multiplexer, choose that input 01, result source is 01, bring that as the value to the register file. It's a little bit loopy, but we're just choosing data as the thing we want to write to the register file. We also are getting the RD field from the instruction, and we need to assert reg write to tell the register file to write this value to RD. Alright, so it seems like we've completed the load word, but we've forgotten about one step. We needed to add 4 to the program counter as well. Now during the fetch stage, the ALU wasn't doing anything else, so we might as well use that time to do PC plus 4. And so back in the fetch stage at the very beginning, we have the program counter sitting here. We can bring that program counter over to the ALU source A mux. We need ALU source A to be 00 to choose the program counter. We want to add 4, so ALU source B needs to be 10 to choose the 4. Tell the ALU to add, so ALU op needs to be 00 to indicate add. That result we want to put right into the program counter, so the result mux needs to be result source 10 to choose ALU result. bring this around as PC next, and then we need to assert PC update to tell PC write to be 1 and enable the program counter to get this new PC plus 4. So that concludes the controller for handling the load word instruction.